Hello and welcome to this talk. The title is Givant, Morley, and Zilber. I hope I pronounced the name correctly. And these are three mathematicians. And I should say from the very beginning that I'm not working actively on this topic. And this talk is a kind of invitation for people to maybe take into consideration these questions and also to it's also a popularization of a series of topics that maybe are less known to category theorists. I would also like to thank the organization of Ithaca 21 for the effort they put, given the complexity of the situation with COVID-19. And so maybe let's start. So my motivation for this talk was this quotation that I found by Giancarlo Rota, and this was his review of the book Toposes, Triples, and Theories by Barr and Wells, I guess. So at the very end of his review in 1986, he wrote, "One or two more books like this one and universal algebra might take off." And this is maybe 30 years later, almost 40, I would say that universal algebra is still with us, and category theory, or say categorical logic, has not replaced universal algebra. And I think it's mainly our fault. Of course, I don't want to push in the direction of a fight between topics of mathematics, but I think category theorists have focused a lot on the general theory and maybe have discarded some questions that I think would really benefit our understanding of universal algebra from a categorical point of view. And so in a sense, this is a kind of Rota's cars, how I call it in the abstract, should guide our work in the future years. And in 2005, Bill Lovier said that it would be nice to have a categorical proof and generalization of Igman's theorem for groups. And the way I see this talk, it really belongs to this kind of questions and motivations, to challenge category theory to solve a concrete problem from which I think there is a lot to learn. And I hope to convince you of this in the next slides. So what's the agenda of this talk? I would like to present a cluster of problems motivated by universal algebra. And I would like to convince you that there is something to learn from universal algebraists. And I would like to provide enough historical framework to really appreciate these problems and understand what's their history and background. So maybe let's start from something incredibly concrete. We start from a unital commutative ring. Then the following are equivalent. Of course, the ring is a field. Every module is free. So these two things are equivalent. And let's see the key ingredients of the implication. One implies two. So we start from a module M, and for every subset A of M, we can consider its span, of course. And then we do a kind of transfinite induction. So we call A0 the empty set, and then we define an to be an minus 1 together with an element which is not in the span of the previous one. So we pick an element from outside of the span. And so this is a transfinite induction where n is an ordinal and it will terminate at some lambda, and a lambda will be a basis of n when R is a field, of course. And so what we learn is that the important ingredient of this proof are the existence of a notion of span and some notion of basis, and the way and linear independence, of course, is a very important is super important in the construction of the basis. So let's try to reformulate this theorem from a more categorical point of view. So consider the monad which takes the free vector space over a set, then the following are equivalent. The free module over a set, I apologize. So the first one is that R is a field, and the second one is that the comparison functor from the Kleisli category to the category of algebras is an equivalence of categories. This is just another way to say that every algebra is free. And for the sake of this talk, a monad having this property, so the property that the functor U is an equivalence, will be called stable. And now question. How do finitary stable monads on set look like? Can we characterize them? So again, these are those monads where every algebra is free, but just looking at the monad, can we understand what kind of monads we can expect to be stable? And also, can we also maybe find all of them, how many they are? And why should we care about those? That's another very important question, I believe. So maybe let's start from a couple of examples. The first example of stable monad are idempotent monads, but there are very few. And then the maybe monad is stable. And if you don't remember what's the maybe monad, it's the monad that sends a set X to X together with a one element separate from the others. So X coproduct determinal. And the algebras for this monad are pointed sets, okay? And this is stable, of course, in the sense that every pointed set is a free pointed set. And do you have other examples, other ideas? Well, there are no other examples. And so let's see what's the theorem. And in 1970s, Givant in his PhD thesis gave a characterization of finitary monads which are stable. So it said that there are precisely 4. And so there is the identity, which is of course stable. And then there is the maybe monad. And then there is the free module over a division ring. And then there is the free affine space over a division ring. And notice that a division ring is just a non-commutative field. So it's very similar to the examples I gave before. And also there is not that much of a difference between the free module and the free affine space. They look very similar. So that's why I said that those were all the examples. But notice that Givant is a universal algebraist, a very good one, actually. I really like his work. And all of this is just formulated in terms of varieties of algebras, and there is no focus on monads, of course, from his point of view. So my question is, why is this true? Why there are so few monads, and how would you show it? Like if I give you a monad with the approach of category theory, can you foresee that there are only 4 stable finitary monads? That's very strange, in my opinion. So maybe let's think, which is what category theorists do better. Let's overthink. And so pointed sets is since quite some time considered to be the category of modules over the F1, the field with one element, whatever that is. So all of these examples look like the modules over some kind of field, something that looks like a field. So among the other things, what's happening here is that the monad secretly encodes something that behaves like a ring, not only a ring, but a field. So how do you show first, how would you find maybe a ring out of a monad? And how would you show that stability forces it to be a field? That's the question from my point of view. And so thus, for some reason, when T is stable, T of 1, A is forced to be some kind of ring, and B contains enough information to recover the whole monad. So I think we need more information, and we only have the example of modules. So let's look at the example of pointed sets. So deeper exploration. How can we show in the most conceptual way possible that the maybe monad is stable, so every algebra is free? And I came up with this idea, which is not very insightful. So I will use spans and closure operators. So I consider a set, a pointed set, x, comma, x0. And for a subset A, I can define span A to be the smallest subalgebra of X containing A. So, of course, given how simple this monad is, this is just A together with X0, and the pointing is X0, of course. And now we can just, given this notion of span, we can just copy the proof that we used for modules over a ring, and actually this will give a notion of basis. And so what's the extraction of a basis? Let's show that every algebra is free. And we do in the same way of vector spaces. And in this case, the basis is given precisely by x minus x0. And this is kind of evident. And also, it's also very intuitive with respect to what we expect. So, okay, this is probably the way I'm telling the story, but I would say there is enough evidence to say that a notion of span and a notion of maybe closure operator, the way you want to call it, and linear independence and basis play an important role in this proof. So can we always define a notion of span? And okay, this is a mistake with my poses here. So the answer is clearly yes, as I say. So let T be a monad on set and XA be an algebra. Then for every subset A, we consider this diagram here. So what do? We do T of the inclusion. So we get T of A into T of X. And then we compose with the algebra structure. And so we get this map from T of A into X. And then we take the epi-mono factorization. And of course, there are many choices. Maybe you prefer regular mono, strong mono. Choose the factorization you find more natural for the moment. It doesn't matter really. And so I call span A the mono into X. And so similar ideas have appeared in the literature, but never the same. And I would refer mostly to Tolan and others. And they call them closure operators for very good reasons. And this notion coincides with the previous notion in the case of vector space and pointed sets. This is a kind of intuitive notion, in my opinion. And so now we can also define a notion of generator and notion of linear independence. So A is a generator if the map from span A into X is an epi, and the elements of A are linearly independent if E instead is a mono. And again, when one checks these definitions, they really do what they should be doing. And I cannot give a reference for this because I haven't found it. I mean, this is something I worked out and it's not written anywhere. And other notion of basis have been proposed. And for example, Jacob says a very different approach for the notion of basis for a monad. And so I don't know if this technology that I suggest is the best one. Just if you like the narrative of this talk, maybe you might like these ideas, but if you don't, then you should also consider other points of view like Jacob's one. So now we have a notion of span and actually also a notion of generation and linear independence. And so, of course, we have a notion of basis for every monad. And so maybe this can be an approach to characterize stable monads and show that there are not that many in set. Actually, if you look at the literature, the Givant approach is kind of similar to this one. It follows this kind of intuition. So it seems that we can generalize the main ingredients of the proof. And let's see a little bit of structure of this things that I defined. So if T is a finitary monad on set, then the span operator from the power set of X to the power set of X is a monad, so it's a closure operator, and it preserves directed colimits. And so this is where we have a connection between the monad being finitary, so preserving directed colimits, and the span operator preserving directed colimits. And so now that we see this kind of span operator, which is defined from in a tautological, I mean, in a very intuitive way from the previous span operator, we can give a definition. And because every monad equips the underlying set with a span, so we give the definition of Morley. And a Morley is a set equipped with a closure operator, and the morphism of Morley is a function commuting with a closure operator. And again, these Morleys are very similar to things that people have been studying. I will comment on that very soon, but maybe do we know some examples of Morleys? So of course, every topological space is a Morley where we map the space into the set equipped with a closure operator. And the functor is fully faithful by the Kuratowski formulation of continuity. So top is a full subcategory of Moore. And every group defines a Morley by taking the linear span of a subset. And this functor is faithful, so it's not full. And also every category of modules for a ring is a Morley, and this time we take the span. And this functor is again faithful. And then given a theory, we can take the definable closure of a subset, which again gives a faithful functor into Moore. And so this shows that Morleys can be a representation of the algebraic data of a structure into a more topological object, which is the closure operator associated to the algebraic data. Okay. So in particular, what we showed is that if T is a finitary monad on set, then we have a faithful functor from the algebras into algebraic Morleys. And by algebraic, I just mean that the closure operator preserves filtered colimits, as I said before. And so we have this representation into Morleys. And in model theory, a special class of Morleys, pre-geometries, has been studied by Zilber. And the pre-geometry is precisely a Morley where the Steinitz exchange property holds. And of course, in the case of a vector space, the Steinitz exchange property holds. And so that's why Zilber, who studies mostly this kind of examples, is interested in pre-geometries. Actually, I mean, this is a bit funny, maybe pre-geometries were defined by Rota himself. This is an unexpected connection in a sense. And the topic of Zilber, which are Morleys together with Steinitz exchange property, goes under the name of geometric stability theory, which is where I took the word stable in a sense. And the word geometric is because we have this closure operator that looks like a vector space. So that's why they call it geometric. And there is a very geometric intuition behind the notion of closure operator. And so what's the Zilber motto? What's the Zilber approach? When a pre-geometry is nice enough, then we can find a field and the structure of a abelian group and an action of the field such that the pre-geometry is actually just the spanner operator associated to the field. So you can force you can find a structure of module for that pre-geometry, so that actually the pre-geometry is just the span operator associated to that. And so this is how Zilber, but also Givant, actually prove that there are not that many stable finitary monads, because they say, okay, start from my monad, I associate to it the algebraic Moore toy, and then I show that actually that algebraic Moore toy can only be induced by a ring, and then that ring has to be a field. So that's the way they do it. And I didn't manage to reproduce the argument from a very categorical point of view. So this is where I failed in a sense. And again, Givant follows the same strategy. And their paper are very far from the narrative I'm pushing, because they are not category theorists and they don't care about the categorical aspects of this theory. So until this point, I mentioned Givant, I mentioned Zilber, and in a sense, the shift from Givant to Zilber is the shift from universal algebra to more geometric approaches to model theory. And now we will do our last shift, which is going to be Morley. So where is Morley in this story? And so the question, what kind of finitary monad are such that every algebra is free, fit in the very general landscape of what kind of first order theories are such that there is only one model in each cardinality. Like the first one is a stronger question than the second one, I would say. So only one algebra, which is free, only one model in the given cardinality. And geometric stability theory emerged as a branch of this question, where you have enough algebraic/geometric data in a sense. And so this question, like when there is only one model, was their true motivation of model theorists for this kind of questions. And in 1960, Morley proved that if a first order theory has only one model, so is categorical, this is how they say, in some cardinal, then it has only one model in all cardinals above Aleph 1. So there is this very strong rigidity in first order logic that if the cardinality at some point chokes, then the whole it has to choke in all cardinals. There must be just one model in all cardinals above Aleph 1. And this shows a very strong rigidity of theory with respect to their models, at least in this behavior. So let's try to reverse wrap up this talk. So we are very far from having a complete categorical understanding of Morley categoricity result. Recently, there have been very good developments. For example, Spindola claims to have a very topos-theoretic approach to this, but this is all very green at the moment. And also, I would say there is still a lot to learn, even given Spindola's work. And also the generalization of Morley result called Shelah categoricity conjecture for abstract elementary classes. This is something we understand only partially, in my opinion. And so Becke, Vasey, Rositsky, Lieberman, and of course also Spindola have done several steps in this direction, and we have a partial understanding now. And Zilber offer a more linear friendly or geometric interpretation of categoricity for first order logic via stability theory. And Givant only studies categoricity in the case of universal algebra. And this is, of course, a more approachable framework where we have a better understanding, and the notion of closure operator and things like this behave much nicerly than abstract elementary classes and classes of models. And the whole talk was reading this list bottom up, right? So the reason for which I find this question nice is that I think having a good understanding of this universal algebra problem could have back propagation to higher level of generality, and so give us a more geometric understanding of why Shelah categoricity conjecture is true in a way that is less logical in a sense and more geometric. And also it's as in the case of Morley theorem and Shelah categoricity conjecture have been used in model theory as a source of techniques, because the problem is very hard to solve, and so the techniques that have been developed have informed and enriched the landscape of model theory. And so I think that this question can inform and enrich the landscape of categorical approaches to universal algebra if we choose to pursue them. And so, yeah, I think it would be nice if people start working on this. The only reason why I'm not working on this is that I'm really working just on other projects at the moment. And so I just wanted to advertise the topic, and maybe someone will find it interesting. And in the last slide, I wrote a very short bibliography, but please email me if you want more, because this is far from being sufficient. So thank you very much for the time of following the talk. And yeah, write me if you want to know more. Goodbye. Have a nice day.